Testing, can you hear me? Alright, this video is public now. So I'm going to be learning data structures and algorithm again. I'm going to be reading the exact same book, the one I was reading last stream. I finished most of these chapters. Hold on. Okay, so I learned about binary trees, sorting, word processing. I think uh, when it comes to data structures and algorithms, I think this dynamic programming topic, this would be the last topic in this particular series. And then I think this book also has chapters on software design. I might read some of those chapters as well. So, anyways, dynamic programming. So, I have this open. I want to do some programming in C. I was just testing this. I want to do some program in C and I'll try to code some of them there. Okay. Dynamic programming is an algorithm design technique that can improve the efficiency of any inherently recursive algorithm that repeatedly resolves the same subproblems. Using dynamic programming requires two steps. You find the recursive solution to a problem where subproblems are identically solved many times. Optimize the recursive algorithm to eliminate resolving subproblems. The resulting algorithm may be recursive or iterative. The iterative form is commonly referred to by the term dynamic programming. We will see how to remove redundancy with simple problem computing Fibonacci numbers. Then we impute the knapsack problem and show how it can be solved efficiently with dynamic programming. Fibonacci sequence is typically defined as follows. F1 is Fn minus 1 plus Fn minus 2. F0 and F1 is 1. Here's a natural recursive implementation. So Fibonacci 91 is the largest value that fits in a long. Okay. 1, 2, 1. How much does this cost? How much does this cost to run? Well, the cost to compute the nth number looks surprisingly like the size of that number because the cost would be computed by exactly the same recurrence relation. So, what is the growth rate? Let's start by looking at a bunch of small values. We might be able to use divide and guess with comparing f minus 1 with fn. So fn is this, and fn over f minus 1 is this. So if I have Fibonacci 5, I'll be doing 4, 3. I'll be doing Fibonacci 4 and Fibonacci 3, right? But if I'm doing Fibonacci 3, doing Fibonacci 2 and Fibonacci 1, and Fibonacci 2 will, okay, so 3 will cause 3 recursion, 5 will cause 5 recursion, 8 will cause 8 recursion. Running this output, it appears to settle at a ratio of 1.618, assuming fn divided by fn minus 1 really tends to a fixed value x. Let's verify what x must be. Fn over 2 is equal to Fn minus 1 over Fn minus 2 plus this. Uh, Wait, where did they get this from? Where did they get this from? For large n, we have Fn over Fn minus 1. You get this by multiplying and rearranging this. As n gets big, the two ratios go to x. So if x exists, then x squared minus x minus 1 is equal to 0. Using the quadratic equation, the only solution greater than 1 is this. Therefore, the growth rate is exponential, 1.618 to the power of n. Note that the value is always in the right range, even if the scale is a bit off. Why is Fibonacci recursive so expensive? Primarily because two recursive calls are made by the function and the work that they do is largely redundant. That is, each of the two calls is recomputing most of the series, as is each subcall and so on. Thus, the smaller values of the function are being recomputed a huge number of times. We could eliminate this redundancy, the cost would be greatly reduced. The approach that we will use can also improve any algorithm that spends most of its time recomputing common subproblems. Following slideshow details the redundancy problem. Let's see how the recursive process works when we compute the value for Fibonacci 7. We can build a tree showing the recursive function calls that take place. In each node, the top half in blue shows the parameter values on the recursive call, while the bottom half in red shows the return value for the call. So the root of the tree represents the initial call to the function with an input 7. The first 7 and then 6, 5. Yeah. Algorithm makes a recursive call to Fibonacci 6 and Fibonacci 5. Compute 6, we need to calculate 5 and 4, and so on. Now to finish computing Fibonacci 3, we also have to calculate 3 minus 1 Fibonacci 1. The result is 2. And to finish calculating 4, we also need to calculate 2 because there are two recursions in the algorithm. So it's going to make a tree, right? And this subproblem is being calculated twice. I think one way you can solve this problem is to memorize the answers. Have a global variable which memorizes the answers. Note that the dependency graph was laid out in a one-dimensional table of size 7. Corresponding to the unique subproblem invoked by the algorithm, this table can simply store the value of each subproblem. This way, redundant calls can be avoided because the value of a subproblem which was previously computed can be read from its corresponding cell in the table without the need to recompute again. The table can be used to derive two alternatives but efficient algorithms. One way to accomplish this goal is to keep a table of values and first check the table to see if the computation can be avoided. This technique is called memoization. Here is a straightforward example of doing so. So values n, if it is equal to 0, values n is equal to n minus 1 plus n minus 2. I don't think we don't even need to return anything, right? This version of the algorithm will not compute a value more than once, so its cost is linear. The corresponding recursion tree is shown below. Second technique is called tabulation. The dependency graph must be analyzed to infer an alternative computation order for the subproblems. The only restriction is that a subproblem can only be computed when the subproblem it depends on have been computed. In addition, the value of each subproblem must be stored in the table in the case of computing a value in the Fibonacci series. We reverse the order to calculate the series from a starting point and implement this by single loop. Unfortunately, since it does not have any similarity to the original recursive algorithm, there is no mechanical way to get from the original form to the dynamic form. An additional optimization can be made. Of course, we didn't actually need to use a table storing all of the values since future computations do not need access to all price subproblems. Instead, we could just build the value by working from 0 and 1 up to n rather than backwards from n down to 0 and 1. Going up from the bottom, we only need to store two previous two values of the function as is done by the iterative version. Current, previous, past. And I think we should initiate this on this line, like after this if condition. Current holds the Fibonacci value. I is 3. Previous, current, previous, past. Okay. Past is the new previous. Previous, past stores what previous has. Previous stores what current has. And the new current value is past plus previous. If we initiate them to 1, past would have 1, previous would have 1, and current would have 2. Yeah, guys, I guess that makes sense. Recomputing of subproblems comes up in many algorithms. It is not common that we can store only a few prior results as we did for Fibonacci. Thus, there are many times where storing a complete table of subresults will be useful. The approach shown above to designing an algorithm that works by storing a table of results for subproblems is called dynamic programming when it is applied to optimizing algorithms. The name is somewhat arcane because it doesn't bear much of a similarity to the process that is taking place when storing subproblems in a table. However, it comes originally from the field of dynamic control systems, which got its start before what we think as what we think of as computer programming. The act of storing pre-computed values in a table for later use was referred to as programming in that field. Dynamic programming algorithms also are usually implemented with the tabulation technique described above. We next consider a problem that appears with many variations in a variety of commercial settings. Many businesses need to package items with great efficiency. One way to describe this basic idea is in terms of packing items into a knapsack. So we refer to this as a knapsack problem. Knapsack problem. Is it knapsack? How do you pronounce? Let me do read aloud. Um, read aloud.
I see ideas in terms of packing items into a knapsack, and
A
so we will
knapsack.
refer to this as the knapsack problem. We will first define a
It is
POM.
knapsack. We will first define a particular formation of the knapsack problem, and then we will discuss an algorithm to solve it based on dynamic programming. There are many other versions of for the problem. Some versions ask for the greatest amount that will fit, others introduce values to the items along with size. We will look at a fairly easy to understand variation. Assume that we have a knapsack with a certain amount of space that we will define using integer value k. We also have n items each with a certain size such that item I has integer size ki. The problem is to find a subset of n items whose sizes exactly sum to k, if one exists. For our example, if our knapsack has capacity 5, the two items are of size 2 and 4, then no such subset exists. But if we add a third item of 1, then we can fill a knapsack exactly with the second and third item. You can define the problem more formally as find S1 all the way till n such that K1 is equal to K. So each capacity totals K. Find a subset S such that adding their capacity equals K. Okay. So if capital K is 5, if the capacity is 5, then we can take uh, K2 and K3, or we can take K1, K1, and K3. Can we take items twice, or can we only take it once? Assume that we are given a knapsack of size K, 163 and 10. The capacity is 163 and 10 items of sizes 4, 9, 15, 19, 27, 44, 45, 68, 73, 101. Can we find a subset of the items that exactly fits the knapsack? You should take a few minutes and try to do this before reading on and looking at the answer. One solution to the problem is 19, 27, 44, and 73. Subset of items. Do we have to find all the subsets? 4, 9. Capacity is 10. Int capacity is 10. And sizes is equal to 4, 9, 15. Well, all this. Snack. I don't think I've ever tried this problem, but let's see that. So, what are we supposed to give? Do we find all the subsets that add up to 163? It is 163, right? Why do we do it like this? Um, okay, let me think about this. How do you do? Yeah, define, right? Total sizes is 10. So we take the capacity um and we take this. Well, what are we supposed to return? We need to return a subset of values. A subset of all the things that add up to 163. I have no clue how to do this. Uh, I need to add a return type. But before I do that, size is total. Right now it's null. It's pointer. How about this? Pointer. So what this will do is store a list of, no, this doesn't make sense. Maybe I should make a linked list. Store a list of these sizes total, or store a list of these sizes. Struct, uh, let's say answer. Subset list. I think it's easier if I make a subset list. And then void. Or maybe not. Subset list node. Let's try that. Okay, let me think about this. Yeah, snack capacity sizes. You call the out parameter, right? Out parameter. Out param. The thing we store our answer in. Is this correct? Um, I'm not an expert. I still okay. Let me think about this. This will store our answer, and we need to find all the numbers that add up to 163. I think this is what I'm going to do. I'm going to take 4 away, maybe, or maybe not. Maybe this should be. Am I doing this right? If I take 4 away, then I take 9 away, then I take 15, then I subtract 15 from 163. So each one is going into a recursion. Let me think about this. I have no clue. Um, so I need a list of answers, and the answer will contain each array that stores all the numbers that add up to 163. For example, 1927, 1927, 44, and 73. I have one solution in mind, but it's going to take up a lot of space. But let's just do it anyways. I was thinking of taking one item out first. But what should the return look like? Is this fine? I don't think so. Um, Let me think about this. Maybe it should return void, and this shouldn't exist. It should be our parameter being manipulated. This should be malloc size of, and this should be this. All the answers will go in. So for this subset, we'll go through each subset for int I is equal to 0. I is less than total size is I plus plus. And then we go out. So let me think this through. Um, I will have int temp. Temp is equal to sizes I. Temp is equal to null. And then you put it back in, and then you do the recursion, and then this is temp. So what I'm thinking is that you have these list of numbers, right? We have these list of numbers. So we will take one away. This will go in one recursion tree. with one cutoff. And then there'll be another recursion with the second number cutoff. And then there will be another recursion with the third number cutoff. Right? And then for each of this, there'll be another recursion. Like for this, there'll be another recursion where the second number is cut off. And then another recursion. Yeah, where this number is cut off. So we are cutting off, like we are going this, and then this, and then this, and then this, and then this. So recursion here, recursion here. And if and we subtract the capacity as well. We need to subtract the capacity when we take it off. Yeah. Uh, temp is not null. Size I is null. Size I is null. Size I is null. Capacity minus temp goes in there. So we in that recursion, in that. So for example, initially it's 163. Then when I take 4 away, the capacity should be 159. For this part. Over here, the capacity should be -3 -6, 154, right? Yeah, yeah. The capacity here would be -15. So 153, 148. Hope I'm right. Yeah, you get the point. If it goes if it goes below 1, then we don't do anything. If int new capacity, new capacity, new capacity. If new capacity is more than, if new capacity has a value, so if it's more than 0, then do this. It's more than 0. If it is less than 0, we just skip it. If it is equal to 0, then we add it to our answer, right? Our current answer. Sublist. Um, let me think. I should call this ans. Int ans. It shouldn't be total sizes. It can be less than sizes. Malloc size of Can I store it? It's fine if I store this in the stack, right? Should I just use the heap? If I do this, what happens here? Are these zero initialized? If it's more than zero, knapsack, more than zero. If there is a difference, we do the thing. Um, Let me think about this. If we find just one answer, we should just leave, right? So let's say this doesn't exist. This doesn't exist. This doesn't exist. This doesn't exist. We have just one answer. Let me think this through. New capacity is more than one. If it is equal to zero, else if new capacity is equal to zero, then we break the for loop because we found it. But the thing is, how do we bring it back? How do we add it to our answer? That's what I want to know. Um, okay, let's focus on one answer right now. So ans list node, ans list node. If so, when we do this thing, there would be one particular answer that might work, right? So let's say there is one. So let's say there is one particular answer that works. By the time the capacity is the capacity for that answer would be zero, right? For whatever answer, the capacity would be zero, and then we would unwind. If it is zero, we say that it's zero. Hold on, hold on. We return. I'm using C++20. It has a boolean, yeah. Boolean knaps, and then we return true. We return true. We do return true, but we need an answer. Struct ans. Aunts list. Malloc. Size of out parameter. Now let me think about this. The capacity is equal to 0. We return true. Um, Otherwise we return false. We return true and we add it to our other thing, our out parameter. We have one node which is the header node. We can forget about that and then we will make a new one. So this node struct is equal to what temp is. Hold on, hold on. How do I add to aunts? Wait. Void add aunts int aunts. Struct aunts node need aunts node is equal to, actually it's a pointer, so it's equal to malloc size of this aunts node aunts is equal to the input value, just so I don't get confused. If there is something on the next list, if wait, we need this. If out parameter nextness, if it has a value, then stamp goes here. The stamp goes here. And if it has a value, no, I got this wrong. We don't need temp. Arts node. Arts node. Next list is this. There. So it's if it has a next value, this has a next value. Aunt's node's next value will take that. Uh, there is something wrong here. Hold on. Suppose this is our current list. If we add a new answer, we create the new answer. This is our current list. And then we have a header over here. We have a header. This is the out parameter. And then we write our answer here. Aunt's next list points to here. That's this line. So if this next value exists, that's this line. Answers next list points here. It's equal to what the thing. Wait. This is the out parameter. Out param. And then this is ans. This is ans. So next list becomes what this has, and the next list of this becomes aunt's node itself. Yeah, I think that would fix it. But what if it doesn't have a value? Else, if it doesn't have a value, is equal to aunt's node. But then I don't need to do this, right? So anyways, this, if there's a new capacity is equal to 0, we add it to our answer. We add it to our answer. We add it to our answer. And this over here, if knapsack returns true, if this returns true, then we add it to our answer. I don't know how well this is going to work. Wide view aunts. Aunts list. This is null. While while this is true, current answer is answer list. Keep going next. Value is null. So this is null. Otherwise, it has a value. Um, if no, it might be the header value also, right? The header value doesn't have anything. So if the next list exists, current list, no, it is answer list. We go next. If hold on, next exists. If next exists, we go next. Then we print its value. We print the value of the current one, and then in case of the header, I'm adding this. I'm adding this cause. So if printf percentage d space, and then you go next, and then you print the answer. If the next list exists, we go next and we print the answer. Yeah, that makes sense. So starting from here, next exists, we go next, we print answer, we print this value. Then next still exists, we go next, we print this answer, next exists, and then this keeps happening until we reach over here. So lastly, it will print the value of this one. It will reach the end, so it won't print anything after that. Now let's see. Time for the big test. Test.c. See if there's any compilation error. A lot of them. Okay, let's see. Implicit declaration of function malloc. Include stdlib. Assignment from int to void pointer makes integer from pointer. Sizes I is null. Line 31. Sizes I is null. If I forgot this. Sizes. We are assuming that sizes wouldn't be 0, right? Null 53. Let's do this 0. Sizes 55, 23. Um, what is the issue? I don't understand. Argument passing argument 2 of caption discards count quantifier from pointer. I should remove the count. There is also a wall, right? The wall switches on the warnings, right? If I do A, it prints nothing. Uh, view aunts list. How do I switch this off? And what was happening here? Add aunts, return true. Current aunts node, next list. Aunts node aunts. I think it's this. Four, 15, 19, 27, 44, 54. 4, 15. I have a calculator. Plus 19 plus 27 plus 44 plus 54 is 163. Okay, so this works. But I feel like this is really inefficient. Hold on. 19, 27, 44, 73. If you tried solving these examples, you probably found yourself doing a lot of trial and error and a lot of backtracking. To come up with an algorithm, we want an organized way to go through all the possible subsets. Is there a way to make the problem smaller so that we can apply recursion? I do that, I want to think about how I can return a list of answers. Uh, a list of answers. Maybe the recursion level, maybe not. Let me think. If new capacity is 0, sizes is total sizes. Think I have an idea. Sizes is total sizes. Okay, I think I have an idea, but it's going to be a strange idea. Uh, Not exactly ants, but value. This is going to be like this. Okay, let me think this through. Um, I have a list of answers. We return true over here. We add an answer and then we return true. Maybe we add the recursion step. That's what I'm thinking. We add the recursion step. Suppose there are two solutions that work. There's a solution over here and there's a solution way deeper over here where the capacity becomes 0. Thing is, if I unwind, how do I add it to the thing? You essentially have two paths to the input, the knapsack, size k, and the n items. It will probably would not do us much good to try and break the knapsack into pieces and solve the sub pieces, since we already know that knowing the answer for the knapsack of size 163 did nothing to help us solve the problem of for a knapsack of size 164. But I mean, we can add, if new capacity 0, then we can just continue because there's no point going down further down the recursion. We need to add the size back in. And you can do that. Would that matter? Yeah, it would. Let me think about this. But we don't add the answer. How about we make another copy of, like, if this new capacity works, we add sizes, but all the correct values are 0, right? But we also have the original with us. Hold on. I think I have an idea. What if my answer is a tree? A general tree. Like, let's say we have tree, and then this is the first part of the answer. Yeah, so for example, let's say 4 is one of the answer. We have 4. And let's say in another list of answer, there's 1944, 1944, and 101. So we are starting 4 list, and then each list is divided into further true. So let's say 19 and 54. So there would be this list and this list. I guess that's how we can make an answer, right? We can add it to the tree or we can remove it to the tree, right? Yeah, I think that makes sense. So our answer is different now. Our answer is a tree. Construct ans tree. Um, Node, we have the root node which contains no values, which is just a 0, but int value. We have the value of the node and we have the children of the node. It's not exactly the next node. It's more like the children of the node. How do I do this? Struct aunt's tree node and siblings, right? Right sibling, leftmost child, leftmost child, leftmost child. So the children of this would have the leftmost child and a linked list over here. So all of these are on the same level. It would be like this. This is the first list of one answer. This is the first list of another answer. This is the first list of another answer. This is the first list of other answer. There can be many sublists where the first answer is 4. There can be many sublists where the first answer is 19. Can be many sublists where the first answer is 44. Like that. And then this would also have children. I mean, it looks confusing, but get the you get the point. Right sibling. Right sibling is null. Okay, we need to remove this. Aunt's tree root. Malloc this. Wow. And then it has no children. So leftmost child is null. View tree. Aunt's tree node. Subtree root. Temp new capacity. Okay, wait. Let me change this. Temp new capacity. Size is 0. Continue. If size I is equal to 0, then just continue. Temp size I 0. I don't think we need this. We don't need, for example, here cancelling out 4. We can keep 4 cancel. We can keep 4 cancel, right? And then make sublist out of these two. Yeah, we can keep 4 cancelled. We don't need to uncancel it. Or do we though? Let me think. 9, 4. Oh, it's going to cause the same problem again. Where the recursions are working with the same sub problem. Okay, maybe let's see what they're doing. So what can we say about solving the problem with or without the nth item? This seems to lead to a way to break down the problem. The nth item is not needed for a solution. That is, if we solve the problem with the first n minus 1 item, then we can solve the problem where the nth item is available. We just ignore it. On the other hand, if we do include the nth item as a member of the solution subset, then we now would need to solve the problem with the first n minus 1 items. A sack of size k minus k n. To organize this process, we can define the problem in terms of two parameters, the knapsack size k and the number of items n. Then on the given instance of the problem as p and k, now we can say that p and k has a solution if and only if there exists a solution for either pn minus 1k or pn minus 1k minus kn. No, wait. If I remove the 4, then it would be, if I do this, oops. When I do remove the 4, it's a completely different problem, right? No, I think then my solution could work. Then it's no longer the same problem. Eh? So size capacity 0. And then you put the size back. So what basically I'm doing here is that I remove 4, do the recursion. I put the 4 back and then I remove 9, do the recursion. Let's see. New capacity. New capacity, capacity minus temp. Size I is 0, we put the size back. But this return true is what confuses me. So if the capacity is 0, return true, we don't need to do anything else. And then we add ons. If the capacity is more than 0, we add it to the leftmost child of the root tree. Add it to the leftmost child. add child void. Int and subtree leftmost child. If leftmost child is null, right? If it has a leftmost child, new tree malloc size of root subtree root leftmost child new tree. In that new tree, the new tree's leftmost child is null. And value is the input value. Now, if it already has a leftmost child, what do we do then? It already has a leftmost child, and this should be in here. It already has a leftmost child. And right sibling is null. So if the root tree has a left child, the root tree has a left child, then right sibling comes what the child of this thing has. And regardless whether or not it has a leftmost child, the new leftmost child becomes this new tree. But this is what's worrying me is that I have another idea. We can check among the children if that value exists. Check var in children. I think this way we can avoid the sub problems maybe. Or maybe not though. So temp new capacity. If the new capacity is 0, I think let's do the 0 case first. I think that's easier. If the capacity is 0, then we add the child. We add the child with the value we just removed, temp to the subroot tree. We continue. Do we need all this continue? We don't need continue, right? Capacity is 0, add child, and then we go to the next one. And let's say now capacity is more than 0. Then we do knapsack with the new capacity. We bring the sizes in, and then we don't do this root, we do the new root. So if capacity is more than 0, we add the root. We add the root. Okay, so we add the child because it could be a potential solution. So this returns struct return new tree. Pointer to new tree. New tree. So the new tree is this. Now new tree goes here. Subtree root. Oh no, wait. New tree root. Now if we do knapsack of this thing, knapsack of this thing. And we are assuming that all the values are unique, right? So if one of the values brings the capacity to 0, then none of the other values would work. So I think it's better if this returns true. Return true. Now if this knapsack thingy works, then we still need to try it with all the other values. With the new tree root. New tree root. Let me think. Let me think about this. If it returns false, if this works, return true. Else, we need to remove the thing first. The question is, how do you remove the child? Um, Free this. Actually, no, this is not how we delete a child. Delete child. Parent. Child. If you want to delete the child, But the thing is, how do we get the. We are assuming that the values are unique, right? So to delete is equal to child. If to delete, actually, it's parent leftmost child. Parent leftmost child, if to delete value not equal to child value to delete becomes the right sibling. So if it has a right sibling, now after all this, we do free. We do it. No, but the right sibling needs to match. So we found. Wait, should be before delete. Hold on, no. No, this is wrong. I want to find a value that's before delete. I have an idea. If let's do the leftmost case differently. If parent leftmost child's value is equals to child val, then this comes null and child, we free the child. To delete, then this becomes before delete. We still free the child. So before delete is the leftmost child before delete if it has a right, as long as it has a right sibling. This can go wrong in so many ways. I think this makes me more comfortable. Before it has right sibling, and the right sibling's value is the child. It has a right sibling, right sibling's value is the child. Then this before okay, that makes sense. The right sibling before the delete becomes the right sibling of the child because the child is going to be deleted. Free and then free the child. And I need to put them in a bracket. So I got this. I added the child. If knapsack this works, if this works, but the thing is, I need to know if it works with the siblings as well, in the other values in the array. So we do this. We don't need to return true. We just add the child. No, actually, we just return because we ended over there. Do we? No, we don't. Because we still need to check. Maybe like uh maybe like with this value it reaches 0, but this value can still keep going, right? So that's why we don't return the function yet. We still keep looping for the other values. Else if new capacity is more than 0, new you make the new root, do this thingy, and check if the new root has any left sibling. If it has nothing, then we delete it. Delete child. Yeah, we delete this. There's no return. Else we just put the size back. Not else. We generally put the size back. If it's more than 0. It's more than 0. But if it's less than 0, then don't bother putting it back, right? Don't bother putting it back so we can skip it next time. Now the thing is for view tree, view tree has nothing. View tree is not. Uh, how do I view the tree? It's a general tree, right? How do I view a general tree? So I print the root. I print the leftmost child. Root is at level 0. Int level. If no, first we print value, but the root should print nothing. But that's fine. Now if it has a left child, if it has a leftmost child, now while it has a right sibling, we keep going by while this is not null, right? So what we are doing is so this is level 1. Level plus 1, current child, current child. Print D, print D. Void function add child 1910. What's the issue? So pointer. Oh, whoops. Parentheses around our assignment user truth value. Implicit declaration of function print. Did you mean printf? Yes, I did mean printf. Control reaches end of non-void function. Delete child 34 1. What's the other one they said? 23 7. Oh, this. Oh, good thing I had the warning on. Zero, zero. Print f percentage d sizes I. Why does it say 0 0? If the new capacity is 0, add child. View tree 0. Level 0, value 0. It doesn't have a leftmost child. Does it even add the child? Subtree temp and then new tree root. Okay, let me see when are they calling this? Print f percentage d space. Okay, it does add the child. So why doesn't it show it here? It does add children, but does it delete children back? I0. Okay, this is confusing. If the leftmost child has nothing, is empty basically, then we delete this child. Yeah, I don't know where the problem is going wrong. Delete the chat. Yeah, how about this? How about 4, 2, 1, and this is 5. Now let me go back up. Zero, zero, level 1, 2, 1, 2. If I have 3 over here, what happens then? 2 and 3 is not even included. So if it's like 5 minus 2, which is 3, so this 2 will become 0. Then the capacity will be 3. And then this recursion will happen, right? Then the new capacity is 3. So, and the new sizes list is 4031. And then within the recursion, when you go through 4031, when you go through 3, you add the child. And then when we unwind, well, first we add 2, but then within the recursion, we also add 3, right? Four, two, three, one. If I have 2 here, 4 here, how would that work? What 1 here, 2 here? Five minus 1, 5 minus 2, 5 minus 3, 5 minus 4. What is going on in here? Let me see the recursion actually. Print f capacity percentage d. sizes I percentage D and slash n. First it goes through 5, 1, and then the recursion happens, so it goes through 4, 2. Then the recursion happens. Zero, 1, 3, 2. 1, 2, 3, 4. 1, 2, 3, 4, and then the recursion happens, 1 gets kicked out. The capacity is 4, 2, 3, 4. 2 gets kicked out. We subtract 2, 0, 0, 3, 4. None of them work. So it unwinds, right? Why does it say capacity 2 again? 0, 0, 3 work, 3 doesn't work. 4 doesn't work, so it unwinds. It's better if I do it here. One, two, three, four. 1 gets kicked out. 0, 2, 3, 4. And then it goes into the recursion. We have 0, 2, 3, 4. Then 4 minus 2, the capacity becomes 2. So 0, 0, 3, 4. So these 3 won't work. Actually, I think it was better when it skipped the zeros. One, 2, 3, 4. 5 minus 1 is 4. Capacity is 4. 4 minus 2 is 2. Capacity is 2. 0, 0, 3, 4. 0, 0, 3 and 4 is not going to work. It's going to go in this else case. So 3 is not going to work. 4 is not going to work. It's going to unwind. It unwinds all the way till 5. Shouldn't it unwind back to 3? No, it unwinds back to 4. How is this possible? 5, 1, 2, 0, 0. Capacity, Achad. I don't understand this step. 2, 0, 0, 4. This I understand. But when it unwinds to 4, right? 2, 0, 0, 4. And then this becomes 0. Okay, let me add a level to this. Gas tank, level 0. Int level. Level plus 1. Level. Zero, 1, level 2, level 2, level 0. Why is level 0 doing this? Uh, level 0, 5, 1, 2, 0, 0. Think it did 5 minus 3 maybe. No, but that doesn't make sense. So recursion level 0, recursion level 1, 2. Then it goes back to 1. You know what? I should also put I in here. Zero, capacity 4, 1. And then recursion level 2. 0, 1, 2, 3, 0. How is I 4? Um, shouldn't I be at max 3? 0, 1, 2, 3, 4. Oh, wait, the total sizes. I forgot to change this. Total sizes here is 4. Now let's say 0, 0. We have 1, and then we have 0. 1, 2, 3. And then we start with 2 because 1 has already been done. But the thing is, what confuses me is why are these two 0? Is it because they became 0 in the previous iteration? Hold on, how do you copy the thing? How do you copy an array in C? Let me see. Copy array in C. Mem copy. I will just write my own. Set array values source destination int I is equal to 0. This again. Int destination I is equal to source I. Int mu sizes is the destination. Does it copy by? Can't remember whether it copies by 1 4 1 3 2 2 3 1 4. Okay, so what the output is? The output is correct. I will just explain what the output is. So, like this tree over here, it starts with 0 0. I put this at the side, which is the root, and then time for the answer. So at level 1 we have 4, and then below that we have 1, and then unwind we have 3 2 2 3, and then 1 4. I think the problem with my solution is that it doubles the count. Like there are twice as many solutions over here. If I do 10 and 163. I don't know if this how well this would work. Didn't work at all. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 1, 2, 3. Yeah, there are 10 values. We don't need this level. Let's say I have 10. I have 4, 6, 2, 8, 5, and 3. So 6, 3, 1 could work. 6, 3, 1 could work. 6, 4 could work. I want to see if it does that. Forget 5. 1, 2, 3, 4, 5, 6. Let's see what does it output. 0 level 1 is 1, 3, 2, 4, 4, 2, 3, 1. Yeah, this adds up to 10. So going back to level 1, 2, 3. No, the other 3. So 2, 6, and 4 are siblings. So 1, 3, 6. Yeah, that works. 1, 3, 4, 2. That works. That's it, right? Is there one which has 6 at level 1? 6. Why is there a big gap? So let's see. 3 is at level 1. 1 is at level 1. What about 4 and 6? Okay, so if I consider 3, 3, 1, 2, 4, 3, and then here's level 2, 6, 1, 6, 3, 1, that adds up to 10. 3, 3, 2, 3, 2, 1, 4, 3, 2, 4, 1, 3, 6, 1, 3, 4, 1, 2, 3, 2, 1, 3, 4, 2, 1, but there's none here which starts with 6. 1, 2, 3, 4, 5, 6. 8 and 2 isn't there as well. It finds some solution, but it doesn't work for all of them for some reason. What happens if I remove this? It doesn't make a difference. Okay, let's see what they made. Hold on. Having solved the previous problem for knapsack of size 1363, how hard is it to solve 164? Try it. Okay. If P n minus 1k has a solution, then P n k has a solution. Else, if n minus 1k minus k n has a solution, then P n k has a solution. Else, P n k has no solution. Wouldn't it be better to indent else with this if over here? Although this algorithm is correct, it naturally leads to a cost expressed by recurrence relation this to the power of n that can be pretty expensive. But we should quickly realize that there are only n k plus 1 subproblems to solve. Really, there is a possibility that many subproblems are being solved repeatedly. This is a natural opportunity to apply dynamic programming. We draw the recursion tree of this naive recursion algorithm, derive its corresponding dependency graph. You notice that all the recursive calls can be laid out on an array size n times k plus 1 to contain the solutions of all subproblems. P I k. Consider the instance of the knapsack problem for k is equal to 10 and 5 items with size 92741. The recursion tree generated by the recursive algorithm follows, where each node contains the index of the object under the consideration from 0 to 4, the size available of the knapsack 310, 210, 010. Return value is no solution. 08, about 08. Now we can make the second recursive call for Pn minus 1k minus kn. This is asking whether there's a solution using the item at index 0 if you have used the item at index 1. So the call is to P08. The initial k is what? 10, right? 0, wait. K1 is 2, K0 is 9. K1 is 2, K1 is 2, 3. But this is what I was trying to do. I don't know how it works. Dependency graph for this problem instance uh, laid out in a table of size n times k plus 1. K plus 1. Or what if we want to find all the solutions, not just one? K is 10, right? And 7 to 1. What about 7 to 1? 7 to 1. 7. K is equal to 7 to, no, wait. 7 plus 3. As I mentioned above, there are two approaches to actually solving the problem. One is to memorize, that is to start with our problem of size p and k and make a cost to solve the subproblem, each time checking the array to see if a problem has been solved and filling in the corresponding cell in the array whenever we get a new subproblem solution. The other is tabulation. Conceivably, we could adopt one of several computation orders, although the most natural is to start filling the array for row 0. We then fill in the successive rows from I is equal to 1 to n. In other words, a new slot in the array gets its solution by looking at most two slots in the preceding row. Since filling each slot in the array takes constant time, the total cost of the algorithm is theta nk. Many engineering problems require multiplying a lot of matrices, sometimes really large matrices. Turns out to make a big difference in which order we do the computation. Turns out to make a big difference. It turns out to make a big difference in which order we do the computation. First, let's recall the basics. If we have two matrices, one of R rows and S columns and the other of S rows and T columns, then the result will be a matrix of R rows and T columns. What we really care about is that the cost of the matrix multiplication is dominated by the number of terms that have to be multiplied together. Here it would be a total cost of R times S times T multiplications. The other thing to realize is, of course, it matters whether we multiply A times B or B times A, but let's assume that we already have determined the order they go in. And for all our multiplication, we assume that the rows and columns match up appropriately so that the multiplications are possible. Given all that, we still have choices to make if there are many matrices to multiply together. Thing that we need to consider is this. We want to multiply 3 matrices and we know the order. We still have a choice of how to group them. Say they are named A, B, and C, and the order multiplication will be A times B times C. But we can accomplish this by either doing A times B times C or by doing A times B times C. The answer will be the same in the end. However, as we see below, it matters a lot which way we do this in terms of the cost of getting that answer. So, given a sequence of matrices, our goal is to find the most efficient way to multiply these matrices. Example, let's say we have 5. We break the problem down into 2 subproblems. Here, the parentheses indicate that the subsequence of matrices have been grouped together for multiplication. We list every arrangement while remembering that matrix multiplication is not commutative. Firstly, we find the most efficient way to multiply the subsequence B, C, D, E. Also, BC is equal to D can be calculated without further division. BC results in a 2 by 2 matrix, while DE results in a 2 by 3 matrix. Thus, the total number of operations to compute are 242 plus 253 plus 223. CDE can be further multiplied in 2 different ways. Yes, CDE and CDE. Total number of operations to compute CDE are 54. And for CDE are 100. Similarly, we can calculate the total operations needed for BCD and BC times D. Thus, we have to compute the most efficient way to multiply the triplet CDE. Yet, we recalculate the number of operations for CDE as 54 and CDE as 100. Additionally, an alternative way is to group ABCD is ABC and DE. Find the most efficient way. We calculate. Finally, we have determined the most efficient way to compute ABCDE is to partition in the manner A, B, C, D, E. The minimum number of operations required are 76. To solve this problem efficiently, we should notice that there are a lot of duplicate nodes in the recursion tree, but there are a lot of relatively little number of actual subproblems to solve. For instance, we repeatedly need to decide the best order to multiply ABC, and to solve that, we repeatedly compute AB's cost and BC's cost. One way to speed this up is simply to remember the answers whenever we compute them. Whenever we ask the question again, we simply use the stored answer. This implies that we have a good way to remember where to store them. That is, how to organize the subproblems to easily check if the problems have already been solved. This took longer than expected because of the problem. I'm going to post the problem in the comment. Maybe one of you can modify it. Let me know what the solution is. Uh, is there anything else I wanted to do? Okay, I will do another stream because I want to know what these are. I will do one last stream for this topic and then I will end the series there. All right, then I will see you guys next time then. Bye.